So electric potential and capacitor. So in this chapter, we have discussed about the electric potential due to a charge in an electric field. Say example, electric potential due to a charge. So that is the main motto of this chapter. First half of the chapter deals with the electric potential. What is the meaning of electric potential? So we have studied that electric potential is the, so why do we need to know this electric potential? Because if we have the charge, any charge, so because of that charge there will be an electric field surrounding to that. So in this electric field means it is the force experienced by the unit positive charge. That means if you bring any charge to this circle, that charge, the charge which you bring experience the force. So what do we have to do? So if you want to bring any charge, it experiences the force. It may be attractive force or repulsive force. So the thing is, the concept of electric potential is, let us take a point here. At this point, if you speak about electric potential means it should overcome that charge which you bring should overcome the attractive or repulsive force. Because if it is attracted by this q, this charge moves like this. If it is repelled by this q, this charge moves like this. So to overcome either attraction or repulsion, it needs some energy. That energy only we call it as the potential at this point. Electric potential at this point. So for different charge, we need different energy. Say example, if you bring a highly large charged particle means it needs large energy. If you bring the small charged particle means it needs less energy only. So the thing is, the electric potential is the measure of bringing 1 coulomb positive charge from somewhere else to this point. So it is the work done. So work done to bring a unit positive charge from infinity to this point. So this should be very clear. Infinity to this point, that point. Okay. So dV, basically we can write in the form of dV, that is equal to minus EdR integration. So why do we need to do the integration here? Because dV is the work done for unit Coulomb charge. So the basic formula for work done is force into displacement. So force for 1 coulomb charge is electric field intensity, and we know that this electric field intensity or force is keep on changing with respect to distance. So what we have to do, we have to take a small distance to move for this small distance to make this small distance how much work is required, that is dV. Then if you want to find the entire work done from where to where, from infinity to that point, that is located, if that point is located at the distance of r from this source charge, then infinity to r, dV is equal to minus EdR. And why do we put negative here? Because the work should be done against the electric field of intensity. If the electric field is towards this q, means the work should be done to overcome the attractive. If it is repelled, means it should overcome the repulsive force. Anyhow, it is against the electric field intensity only. And here itself we can write E is equal to the rate of change of potential difference with respect to R. The unit of E can be written as unit of E. So basically we express electric field intensity in the formula for F by Q0 in that manner, the unit of E is Newton per Coulomb. And if you want to express electric field intensity in the formula like this, the unit should be volt per meter. So there are two formulas in by this two formulas, two units can be used for electric field intensity. One is Newton per Coulomb and another one is volt per meter. Okay, volt per meter. So in this way, we found two things. One is electric potential due to point charge, okay, this we have found electric potential due to point charge. Say example, if you have charge q and if you want to find the electric potential at a distance of r from q, means the electric potential is 1 by 4 pi epsilon 0 q by r. E is the 1 by 4 pi epsilon 0 q by r square, and in that if you just remove this r, you will get the electric potential. So this is the basic formula, and this potential is the scalar quantity. So if we have the positive charge, the energy will be positive. If you have the negative charge, the energy will be negative. So these are all the basic things about the electric potential. And this point have some potential, and say example, if you consider this point, it will have some other potential. So in an electric field, different points are having the different electric potential. So if you want to move a unit positive charge from one point to another point, you need to do some work. That work is called as the potential difference between these 2 points. If you want to move unit positive charge from one point to another point, you have to do some work. That work is called as the electric potential difference, right? Then the second thing is electric potential due to electric dipole. Electric potential due to electric dipole at any point. Electric potential due to electric dipole at any point. This we did, right? Electric dipole at any point. So in the last chapter, we found electric field intensity due to electric dipole. We derive the electric field intensity due to electric dipole at a point of axial line. So at this point, what is the electric field intensity? And also we found at a point of equatorial line. At this point, what is electric field intensity? So this point is, I think it is 2p by 4 pi epsilon 0 r cube, and here it will be p by 4 pi epsilon 0 r cube, and here the direction is like this. The net electric field intensity direction is like this, and here the direction is like this. So this is electric field intensity we found at only 2 points. One is at the point in an axial line, another one is point in at an equatorial line. So okay, but here we are going to find, and we can also find electric field intensity at any point. Say example, if you want to find electric field intensity at this point, so if this point is at the distance of r and the angle is theta, so if you want to represent any point from the electric dipole, two things are required. One is distance from that point, and another one is angle of the line connecting center of the dipole and the point charge. Angle of line connecting center of the dipole and the point and the required point with the electric dipole. The line connecting OP and the electric dipole. So the angle between these two lines and the distance from that center, that two things are important. So here the angle is 0 degree, here the angle is 90 degree, and we didn't derive electric field intensity at any point from the dipole, but the formula is the same thing, p by 4 pi epsilon 0 r cube only into the factor called 1 plus cos square theta. I'm sorry, 1 plus 3 cos square theta. 1 plus 3 cos square theta. Here, if you substitute theta is equal to 0 degree, then you will get this formula. If you substitute theta is equal to 90 degree, you will get this formula. So this is this one we didn't derive. We didn't have this formula in our textbook. Maybe you may get questions for NEET or JEE. by using this formula. But for our NCERT board exam, I don't think this formula will be useful for you or us. Okay, no problem. Now the thing is, we have derived the electric potential due to electric dipole at this point. So for that, we take this distance as R2 and this distance as R1. Now we found the relationship between this R1, R2, R and theta. From that, we finally derived the electric potential formula. It is P cos theta by 4 pi epsilon 0 R square. This is the formula for electric potential at any point from the electric dipole. Any doubts up to this? Because up to this we've done. Okay. So now, in this case, electric potential due to electric dipole. Say example, for axial line. So let it be case 1. For axial line, theta will be 0 degree. So in that case, if you try to find V value, so what is cos 0? Cos 0 is 1. So in that case, you will get the maximum electric potential, that is P by 4 pi epsilon 0 R square. But axial line maybe two things. Maybe you can this is also axial line and this is also called as axial line. So in an axial line itself, we have two angles. Either theta is equal to 0 degree. In an axial line, if you want to find near plus q, that is theta is equal to 0 degree. For axial line, if you try to find near minus q, it will be theta is equal to 180 degree. So this angle, this for this point, the theta will be here to here, right? So it will be 180 degree. So in that case, if you try to find cos 180 degree, it will be minus 1. Cos 0 is 1 means cos 180 is just opposite to that, minus 1. So it will be minus 4 pi epsilon 0 R square. And now for an equatorial line, third case, for an equatorial line, this line, theta will be 90 degree. Okay, theta is equal to 90 degree. Or if you take equatorial line like this, theta will be 270 degree, 90 degree or 273. Both of that, cos theta, cos 90 or cos 270, if you try to find, it will be 0. So V will become 0. Why V is 0? Because if you keep at the exact center, minus q and plus q, if you keep at the exact center, plus 1 coulomb, if you keep plus 1 coulomb at the exact center, this minus q attracts. This plus q repels. So to overcome this charge, if this charge overcome this minus q, it needs some energy. If this charge overcome this plus q, it needs some energy. But this V1 will be negative and this V2 will be positive. And if you add both the things, because here the electric potential is not the vector quantity, it is the scalar quantity. You can simply add the electric potential. So the net electric potential must be 0 at this point. If we keep that point as if you keep that point as the exact center from the dipole. Is that clear? So for an equatorial line, the electric potential is 0. That means you can simply place any charge. You don't need to give any extra energy to place the charge. Is that clear? Okay, just take a notes. Now, if we have system of charges, like in a place, if we have q1, q2, q3, q4 like that, Because of that, what will be the electric potential at any point? So in previous topic, we have found electric potential due to electric charge, unit electric charge, due to a single point charge, and after that we found that electric potential due to electric dipole. And now electric potential due to system of charges. System of charges means, say in a particular location, if we have charge q1, q2, q3, q4, like that, if we have n number of charges like this, and in this location, if you want to find electric field intensity at any particular point, if you want to find electric field intensity at any particular point, then what is the electric potential? What is the electric potential? So normally the same case we have dealt with electric field intensity. In electric field intensity, we found what is this q1. This we have to check. This q1 is plus or minus. If this is positive, then the force will be repulsive force, electric field intensity due to this. And then for q2, then this q2 is negative, means the e2 will be like this. Q3 is positive, means e3 will be like this. Q4 is negative, means q4 is negative, means it will be like this. So e2 this is e3, this is e4, like that. We just make 4 or 5 forces, so that forces are acting at this point at different direction. Then the net electric field intensity is the vector sum of all the electric field intensity. Why? Because we shouldn't add, we don't add not only the electric field intensity, we have to consider the direction also. If one force is like acting like this and another force is acting like this, means automatically there may be a chance of getting cancelled if both are equal. So the direction you should include. But in this case, electric potential, if you want to find electric potential, you don't need to worry about the direction. So electric potential at P means just need to check whether Q1 is positive or negative. So you have to find Q1 by, so what is the distance between this Q1 and first point? Let it be R1. If this is R2, and this will be R3, and if this will be R4, then we know the formula for electric potential due to a point charge. We know the formula for electric potential due to point charge. So that is Q by 4 pi epsilon 0 R1. For Q2, it will be Q2 by 4 pi epsilon 0 R2. Q3, it will be Q3 by 4 pi epsilon 0 R3. So if any charge is negative, then you have to put negative symbol here. Okay, if any charge is positive, that is positive. Negative means you should add negative here. Don't need to worry about the direction because it is the scalar quantity. You have to add whether the work is done by the system or work is done on the system. There are two things. One is, if the source charge is positive, the point charge, the test charge is repelled. So work should be done on that charge. To keep at point P. Because if you are bringing the test charge from infinity to point P, once it reaches the electric field, once it reaches the region of electric field, it experiences the repulsive force. It experiences the push. Okay, it experiences the push. So it has to overcome the push. It has to overcome the push, right? It has to overcome the push. So the work should be done externally. So that work is the positive. Say example, if the source charge is negative, we don't need to give any external work to bring its test charge from infinity to this point. The test charge itself can be attracted by the source charge. The only thing we have to make sure is we have to keep that point at this point P. It should not go towards Q1. So the work is done on the system. So in first case, sorry, in second case, work is done by the system. Work is done by the system. So we don't need to give any extra work. What we have to do, we have to overcome the energy given by the system. So what energy we need? We need to have the negative energy. It needs the negative energy. So if we give external work, that will be the positive energy. So that only we just put, if it is positive charge plus, negative charge minus. So we don't need to worry about the direction. Is that clear? Is that clear? Okay. Similarly, say example, if I have a object, an object consists of charge. An object consists of a charge. Let it be Q. Charge means the entire charge, the object consists of a charge distribution. Charge distribution throughout its volume. Throughout its volume. Throughout its volume. So say example, let it be plus. So throughout the volume, the charge is distributed like this. Okay, throughout the volume, the charge is distributed like this. Now what we have to take care of is at how much density these charges are distributed. So let me take the charge density as the rho. Charge density as the rho. In the first chapter, we have been studied about linear charge density, surface charge density, like the two terms we have studied. One is linear charge density, that is charge over a length. And another one is surface charge density, that is charge over an area. Here, volume density, here the charges is distributed throughout the entire volume. So it is charge divided by volume, the total charge divided by the volume. And so this Q must be rho into V. So for this case, if you want to find the electric potential at this point, if you want to find the electric potential at this point, so what is the formula? The simple formula only, Q by 4 pi epsilon 0 R. But we don't know, right? We don't know where this R is located. From which point we have to take the distance. So we have to take a distance from this or this or this. So like that it go, right? So the R can be taken from any point from the entire volume. So in that case, what you have to do, you just put here R square and here just multiply R. Just put R square and R here. Then for a small charge dq, what is the total work done? From that you have to do the integration, or take like this, q into dr. For a small distance r, what is the work done? Then from that you have to do the integration, the entire thing. So here the total electric potential can be found by only doing the proper integration. In that case, either you have to know the relationship between this charge and the distance, or the density and charge, like that you have to, or the charge and volume you have to know. Anything you have to know. Okay, so any kind of relationship you have to know. From that only you can find the electric potential. Is that clear? So I'm not going to explain the entire integration process here. For the, as of now, we don't need. But the thing is, if the charge is distributed like this, if the charges here we have the single point charges, Q1, Q2, Q3. Then what is the potential due to Q1? This. What is the potential due to Q2? This. Then add all those things. Here the charge is not like this. Here the charge is continuously distributed. That means at each and every point you are having some charge. We don't know that. For that only they define the density. They defines the charge density. So in that case, we can't find the electric potential due to the charges present in all those points. We can't find the sum of all the electric potential present in the at each and every point. At each and every point, infinite number of charges are present. So it all put together, that is called only Q. This all put together called only Q. So we can't find individual electric potential. So what we have to do, either we have to know the relationship between the charge and volume. So at this volume, how much charge is distributed? So the relationship between volume and charge we should know. If we know that, we can do the integration process here. We can do the integration process. So maybe if you write JEE advanced, you can have the questions from this area. Okay. So for our regular NCERT syllabus, you don't need to worry about that. The thing you have to remember is the electric potential is inversely proportional to the distance between them. V is inversely proportional to the R. This is what you have to remember for a point charge. For a point charge, a system of charges. But for electric potential, for electric dipole means V is inversely proportional to R square. So these two things you should remember. Okay. 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 Now equipotential surfaces. Equipotential surface. So what is the meaning of equipotential surface? See, from a charge, from a source charge, from a source charge, surrounding to that source charge, all the points have some electric potential value. Am I correct? If you have the charge here, means surrounding to the charge, wherever you are having the electric field, wherever the electric field is there, all the points have some electric potential. Am I correct? So the equipotential surface means, let me consider this plus Q charge. Now I will explain it is the 2D diagram, right? It is the 2D diagram. So here I can explain the equipotential line. First, try to understand the concept of equipotential line. What is equipotential line? Say example, from this charge, consider the point P here. So it is at the distance of R, right? Consider the another point, it is also at the distance of R. Now tell me, what is the electric potential at P? It is Q over 4 pi epsilon 0 R. What is electric potential at Q? It is also Q over 4 pi epsilon 0 R. Am I correct? Both are at the same distance, but both are the different points. So now VP and VQ is same or not? Is VP and VQ same or not? They both are same. Okay, so they are the equipotential points. They are the equipotential points. Like that, at the distance R from this plus Q. So the points which are all at the distance R from this plus Q have the same potential. Am I correct? Now this line is called the equipotential line. Am I correct? Similar to that, if we draw the another circle like this from the charge Q, if we draw the another circle like this also has the some other equipotential line. Am I correct? Am I correct? Now it is the 2D diagram. If you consider the 3D, if you consider it in the 3D format. So at the center you are having plus Q. If you cover the plus Q with a ball, if you keep the plus Q at the center of the ball, center of any ball you can take, the surface of ball is assumed as the equipotential surface. Am I correct? Because see, you have the charge, you just keep this charge at the center of the ball, at the center of the ball. Yeah, any ball you can consider, a spherical ball. Okay. Okay, at this center, you are just placing plus q. Plus q. Now, throughout the surface, so this point, the surface of the ball, the entire surface of the ball, the points in the entire surface of the ball are at the same distance from q only, right? That is the radius of the ball. Am I correct? Am I correct? So that surface is the equipotential surface. That surface is the equipotential surface. Do you understand? So in 2D, we can see only a line. But if you consider it in the 3D, it will be the surface. So for a point charge, a sphere will be the sphere with center as the point charge. Center as the point charge is this equipotential surface. Am I correct? Equipotential surface, because all the points are at the same equipotential. Now tell me the potential difference between the 2 points. Potential difference between 2 points in an equipotential surface. What is the potential? What is the potential difference between 2 points in an equipotential surface? What is the value? Yes, tell me fast. What is the potential difference between this point and this point? Why R is R minus R? Here. So both are same means what is the potential difference? 0 volt. That means you don't need to do any work to move this plus 1 coulomb from this point to another point, right? So work done to move any charge. So plus 1 coulomb we are speaking. So like that, if you keep plus 5 coulomb also, you don't need to do any work. So work done to move a charge in an equipotential surface. What is the value? What is the value? Yeah, 0 joule only. Because potential difference is 0 volt. Potential difference is 0 volt means so you don't need to do any work. But at the same time, so if we have the some other equipotential surface, let me draw like this. If we have the some other equipotential surface, this is at some extra distance. So if we say this was R1 means this is at R2, and this is also an equipotential surface, right? So if you want to move a charge from here to here, you should do the work, right? One equipotential surface to another equipotential surface, you need to do work. But within an equipotential surface, you don't need to do any work. That's the concept. Okay. So for a point charge, surface area of all concentric spheres. All concentric sphere. Concentric sphere means, so this is plus q. If you surround this plus q with one ball, that is concentric sphere 1. If you surround that ball with another ball, that is concentric sphere 2. If you so all the concentric spheres are the equipotential surface. Surface area of all concentric sphere surrounds the point charge or equipotential surface. Is that clear? Okay. Then, okay, say example, if you have the charges distributed in the line, then the surface, equipotential surface must be the cylinder. Okay. for a line distribution, for a line distributed charge, the equipotential surface must be what? Equipotential surface must be a cylinder with the axis kept at that line. Cylinder that is having the center axis kept at that line. Is that clear? Okay. So similar to that, you can look at your book figure 2.11. So they try to correlate the equipotential surface for a dipole. They will try to explain here. In that case, the circle is somehow oval, so it is not at the exact center. The minus and plus, if you look at exact minus and plus, see, that is minus q and this is plus q, so this is the dipole. See, this is an equipotential surface for this minus q, and this is an equipotential surface for this plus q. But if you just try to draw the big circle, so it may not be an equipotential surface because it can be influenced by this minus q. If you want to draw a big circle surrounding to the plus q, it can be influenced by minus q also. Same case here also here. So in that case, if you try to draw the equipotential surface, it is somehow eccentric from the minus q. Here, the same case here you can see. Okay, the plus q will be like this. The equipotential surface somehow will be like this. It is not at the exact center. The plus q will be kept at the one corner of the surface. Is that clear? Is that clear, man? Okay. So just make a note of this and go through the just read the 2.6 and 2.6.1. 2.6.1 also we have finished. Okay, 2.6.1. And in next class we can discuss, maybe Friday we can discuss 2.7. Okay, so tomorrow we are having chemistry class, and day after tomorrow we will continue this session. Okay, and